Okay, so let us begin our week 4 tutorial for this course that is in magnetism and superconductivity. So again there will be 10 questions and I will be solving them one by one. So basically this tutorial is mostly focused on the week 4 topics like Ising model. Mainly Ising model based questions are there. So we'll try to solve them. So first look at question number 1. It says that which of the following is or are observables in an Ising model. Four options are given. One is energy, second is chemical potential, third is magnetization, and fourth is all of this. Okay, so you have energy, you have chemical potential or mu, you have magnetization A, and the fourth option is all of this. And the question is that within these options, which can be established as an observable in an Ising model. Okay, so first I'll tell you the answer. The answer will be all of this. Now let me tell you the explanation why it should be the case. So first of all, you have to know that what is meant by an observable in Ising model, right? So let's say what is Ising model first. So I'll not go into details of Ising model because that is already what you have probably studied in the lectures itself. But just to write down the basic structure of the Hamiltonian Ising model, I'll just write down that much because that will be essential. So let me first write it down. So let's say we change it to this external field, we change it to small h so that there is no confusion between the Hamiltonian h and the field h, right? So from 1 to 8, this one. So this is the Hamiltonian for an Ising model, standard Hamiltonian form. You are probably familiar with it. Okay, so this h is means Hamiltonian, and this first term is coming from the nearest neighbor interaction term. So this ij in this bracket means the nearest neighbor interaction between the spins Si and Sj. Nearest neighbor interaction between the spins which are nearest neighbor to each other, which are in this case Si and Sj. Okay. Sum over all those terms. This J is the exchange interaction strength of the spins. Okay. So this denotes the strength of the exchange interaction that happens between these nearest neighbor spins. So we call it exchange interaction strength, where we know that if J in this structure is greater than 0, that means the system is ferromagnetic, and if J is less than 0, then the system is antiferromagnetic. And why so? Because this JSISJ, now there is a negative sign already in front of it. So, sorry, negative sign already. And if the system is ferromagnetic, then the spins will be parallel to each other. That means both Si and Sj will be either spin up or both will be spin down. That means their product will be whatever spin there, either both are spin up, then plus one and plus one makes the product plus one. And if they are spin down, both of the spins are spin down spins, then minus one into minus one also gives us a product of plus. So this thing will always be of a positive sign from here. Now we know that for a ferromagnetic system, the basically the stable state is where the energy becomes a minimum, right? And in this case, the energy will become a minimum if there is a negative sign in front of it. That means that if there is already a negative sign and you are getting a positive sign from the product of Si and Sj, then the remaining term, this J, should be greater than 0 to make the whole term as negative. So from there we can say that this is the lower energy state or relatively steady state, which is actually justifying it to be a ferromagnetic state for J greater than 0. Because we are saying that the spins are parallel to each other, making the product Si and Sj as plus 1, right? Now, at the same time, if on the other hand, if you consider the case when J is less than 0, then what happens is that uh, that is favorable only for the case if the spins are anti-parallel to each other or the system is antiferromagnetic, because then only we can get a lowest energy state or minimum energy state out of that, right? So, like if say the spins are anti-parallel to each other, that means Si and Sj will have opposite signs to each other. That means if one is plus one or upspin, then the other will most definitely be minus one or downspin. So their product will always be minus one from this Si and Sj product. And there is already a negative sign in front of it. So this minus and the product SiSG's minus sign compensates each other to make the whole term as positive. Now, to make it a stable state, the energy has to go through a minimum. That means this should be a negative sign overall. So the only remaining term that can do that is this J term. So in this case, we must choose J to be less than 0, and that makes the system antiferromagnetic as a stable state. Right? So this is the explanation. I am sure that you have already been familiar with that, but still I have explained it once again. And now the second term is already well known. The small h is the external field. So I have put it somewhere. It is also taken as capital H as well, but in this expression I have used small h so that there is no confusion between this Hamiltonian capital H and the external field small h. And SI is the individual spin. So we are taking sum over all the individual spins. If there are total n number of spins, then we take a summation from I equal to 1 to n. And this is from the external field acting on each of the individual spins, the second term. And the first term is basically what is the exchange interaction strength between the neighboring spins. So first term is the interaction between the spins term, and the second term is the individual spin, how they are affected or how they are influenced by the field that is externally applied to them. So this forms the Ising Hamiltonian in this case. And also, as I said, that this SI should always take the values plus 1 or minus 1. These two values because they are Ising spins. So these are the two values that are two spin states or two values that are allowed for Ising spins, right? And we can also think of it like, let's say this is a lattice kind of structure made here, and you want to see that you have placed your one spin, you are looking at this spin here. Let's say this is your SI at the ith position. Now, if you look at 2D, because we have drawn the structure in 2D, so then we have to look for what are the nearest neighbor spins for this SI spin, particularly SI spin, to for this first exchange interaction term, right? So the nearest neighbor spins for SI will be sitting here, 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 and here. So these four will be the nearest neighbor spins corresponding to this position of SI. So 4 nearest neighbor, I am short in abbreviation writing it as n dash n. So 4 nearest neighbor spins to SI, and these 4 spins will actually contribute to the exchange interaction with a strength of J for SI, right? Now we can also say that why these positions are not nearest neighbors. So that is very evident because you are just looking at 2D. So it is like a lattice structure. So closest to this SI are these four red colored circular spots, which are all equidistant from SI, and they are the minimum distance possible for a spin to be positioned from SI. If you go at this position, or let's say this position, then the distance is greater than the this amount of position, because if this is a square lattice, then let's say this is your A distance and this is also your A distance. So all these four spins which are nearest neighbors marked by red are placed at distance A from the main center spin that we are concerned about, which is SI. Now, if you just look at the distance of another spin, this point from SI, you will see that this is basically at a diagonal position from SI. So this is like a diagonal length of this square, which has side length of A. So this length will be A times root over of 2. That means it is a greater length. So obviously, only these four positions will be the four nearest neighbors, and this position or this or anywhere farther than this will not be a nearest neighbor to SI, and since because of that will not be contributing to the first term. Okay, so this was our main idea of Ising model and the basic structure of Ising Hamilton. Now let us go to the question that we need information about the quantities of like energy chemical potential, magnetization, etc. So first of all, if this is our Ising Hamiltonian, then we know that this will be like a canonical ensemble, right? So this will have a partition function as well for the system. So we'll consider a canonical ensemble for the system, and the partition function Z will be of this generic structure that sum over R e to the power of minus beta ER, where ER is each of the individual energy levels that are possible for this case. Okay, and sum over R means we are taking a sum over all the possible energy states. So these are the energy levels, and beta equal to nothing but 1 by kBT, where kB is the Boltzmann constant and T is the temperature. So this is the partition function for this canonical ensemble case. Now we can also define a free energy for this particular ensemble, which is given as F. F is your Helmholtz free energy, which is written as minus kBT ln Z for this canonical ensemble. So this is your Helmholtz free energy written as minus kBT ln Z. So it is a logarithm taken over the partition function with this kBT term, which is basically 1 by beta. So that means your F is equal to minus ln Z by beta, right? So you can consider that your F is some because this is basically energy, right? So you can consider this is an energy equivalent term for this particular system. So this is energy equivalent, and you can see that it is dependent on the partition function by a logarithmic relation, that is ln Z for this Ising model system, right? You can also look at it in a way that you can take the energy as an average energy for this particular case, because that only thing you can measure, the only thing that is a measurable quantity in this kind of systems, which is basically calculated statistically, so you have to take an average over that quantity. So because it is an ensemble, right? So you cannot just take individual energy, you have to take, you have to measure an average energy, and that is given by this sign, either this or this. So this is your average energy of the ensemble, which is related to your Ising model system, and this can be written as something like ER sum over R e to the power of minus beta ER. So here e to the power minus beta ER is your weight factor for this particular energy state ER, and then you are taking a sum over all the states, and you are dividing by simply the partition function to take an average. So this is basically your partition function, and you are writing this weighing factor with the each of the energy level like this. So you can also write it like this is del beta of um, del beta of sorry, just 1 second. Okay. Um, yeah, so this is like e to the power del beta of e to the power of minus beta here. So if you have to get a term like this, so then you have to take a derivative of beta, and there will be a minus sign. So to compensate that, we also take a minus sign in the front. So this is del beta of e to the power of minus beta ER. There will be a summation over R term also. And this is the Z term because this is the partition function. So this is like 1 minus 1 by Z, and the upper term is minus del Z by del beta. Or you can rather simplify it further like minus del beta of ln Z. So this is your average energy. You see that this is dependent on a logarithmic function of the partition function, and then a derivative is taken with respect to beta. So this is your average energy. So you can see that both this average energy, and also if you take the free energy, Helmholtz free energy in this case as an equivalent energy form, because it has also the energy dimension, you will see that both are dependent on the logarithmic function of the partition function. Okay, so this is the expression for this energy in this Ising model. Also, to look at the other quantities that we had mentioned in the question, one important thing is the magnetization, because this is a spin system, right? So magnetization is a very important or crucial quantity that is to be measured from this kind of a system. So magnetization is basically normally measured as magnetic moment per unit volume. So this will be like, uh, or you can also say that you can say magnetization is written as the total magnetization divided by your total number of spins. So this small m is equal to capital M, the net magnetization divided by the net number of spins equal to your individual magnetization, which is like small m. So this can be expressed as, so you can either say m or capital M, whatever you want to take for the magnetization value. So basically your capital M is related, expressed as minus del F del H. Okay. And here your H should be tending to 0. Also, no, let me just rectify it so that your field should be, field I have written by the small h in expression. So it is denoted by small h. So your small m, that is the magnetization per spin, total number of spins is the total magnetization, and your small m is magnetization per spin. So m is small m is basically minus del f del h at h tends to 0. So because it is a spontaneous magnetization, so we are looking at when the field small h external field is going to 0, tending to 0, then this spontaneous magnetization is represented as a, this is spontaneous magnetization is represented as a derivative, first order derivative with respect to the field of the free energy, which is basically your Helmholtz free energy, but it is your Helmholtz free energy is capital M, but when you take per spin, so it becomes small m. Okay? So because we are taking small m, so we have to take small f. You have, if you are taking capital M, then we should have taken capital M. So this is the logic. Now this can be expressed like, let's say you know that your Helmholtz potential F is equal to U minus Ts minus mh, where this is basically the thermodynamic relation where U is your internal energy and all the other factors you already are familiar with from the basic thermodynamic relation. So if you take a derivative of it, it becomes dF equal to du minus dds minus dSdt. So I am taking term by term derivative, minus ndh minus hd. Now from the law of thermodynamics, you know that your du equal to TdS minus PdV if it is a like such a system where this pressure and volume comes into the contribution. So if it's like a fluid system, but if it is a magnetic system, then instead of P and V, we have the parameters as M and H because they're the quantities of magnetization and magnetic field instead of pressure and instead of volume and pressure. So in that case, the equivalent format of du becomes TdS minus, uh, so because this was equal TdS minus PdV, but always there is a sign change when you come to from a PdV kind of state to a MdH or UDN kind of state. So that there will be a change of sign. So it will be plus. So this is basically known from any thermal physics idea or thermodynamics. You can look at any book. So you can get this formula how this is coming. But this is TdS plus HDM. So this will be like substitute it here. So this is TdS plus HDM minus TdS minus SPT minus MPH minus HDM. So this cancels out and you get DF equal to minus SPT minus MDH. Right? Okay. Right. So from here you get that your capital M is equal to minus del F del H when dt equal to 0. So this is the partial derivative of the Helmholtz free energy with respect to the field. So again I am again and again writing this external field by capital H. So this basically just understand that when I am using it with M, so this quantity basically means the magnetic field. So don't confuse it with the Hamiltonian H anymore. So just consider that this capital H is denoting your magnetic field. So this is your net magnetization in, and it is represented as a partial derivative with respect to the field on the free energy M. And so if you want to express small m, which is capital M by capital N, magnetization per spin, then you just have to also divide it by a capital N on the other side. So capital F by capital N makes it small m, free energy per spin. So this M is equal to minus del F del H. Now you already know that your capital F is nothing but minus kBT ln Z or minus ln Z by beta. So your M becomes just minus 1 by beta. This minus and this minus cancel out each other, so it is plus. Then del del H of ln Z. So this is the derivative, first order derivative with respect to the field on the logarithm of the partition function. So this is how it is related to the partition function of the Eisenstein model. Now we can also, if you want to calculate what is the how to get the chemical potential, then we can also find out that relation as well. So this is chemical potential or mu. How should we get that expression? So this is basically similar. You have to use a thermodynamic expression or relation. So you know that from thermodynamics, your dF equal to TdS plus mu dF. So your mu will be like del F del N. Where del N, dN is basically the change in the number of particles in the system, and mu is your chemical potential. So mu equal to nothing but del F del N. Also, because you know this is del N of minus ln Z by beta, because you know the expression of A. Okay, so right. Yeah, so it is recording. So this is how your chemical potential is also related to the partition function Z. And similarly, there can be many other possible terms that are relatable for this quantity. But what you want to express is that earlier the question was what are the observable quantities for this kind of a Ising model spin system. So basically, the rule is that any quantity that you can measure from this system, which can be expressed as a either some kind of logarithm of the partition function or some partial derivative of that quantity of that logarithm of partition function, any kind of that property or that quantity that we can get will be considered as an observable for the Ising spaces. So you can clearly see from all these calculations that if Z is your partition function for this Ising spin model, then the energy also has a logarithmic dependence on the partition function, like here energy equivalent, and also in the expression of average energy you have ln Z. And then for the magnetization as well, you get first order derivative, partial derivative of the logarithm function of the partition function. Then similarly, you can also get a similar first order partial derivative expression of the partition functions logarithm form or ln Z. So all of these are satisfying the condition. So all of them are um, like eligible to be called as an observable for this Ising spin model system. Similarly, there can be other examples as well, like the pressure if it is like fluid light system, and if there can be the specific heat or heat capacity, because you know that heat capacity C is related as d E dt. So it is a temperature derivative with, of the average energy, and you know your average energy is going as, so take the expression earlier, minus del del beta of ln Z. So this is d dt of minus del del beta of ln Z. Again, a derivative of the logarithm of the partition function. So all these measurable quantities can be expressed as a logarithm of the partition function Z or a partial derivative of the same. Hence, all of these are observables of this Ising system. So we have learned what are the observables for this case, like the energy is an observable, chemical potential is an observable, magnetization is an observable, pressure will be an observable, and also specific heat or heat capacity will also be an observable for this kind of system. So hopefully this question is clear to you. So then we'll move on to the next question, right? Just give me a moment. And so let us go back and read what was the second question. So the second question is that consider a single atom in an external magnetic field Hm. So the matter is sitting in an external field given by Hm. Suppose that the atom is in the thermal equilibrium with a heat bath of temperature T. So the atom is sitting in a thermal equilibrium with a surrounding heat bath, and the heat bath temperature is T. According to the Boltzmann distribution, the mean spin of the system of the atom, where beta equal to 1 by kT, k is the Boltzmann constant, and u is the magnetic moment of the atom. So we have to calculate the mean spin of the atom, right? Okay, so question number 2 says that this is, let's say, your atom that is mentioned in the question, and it is in thermal equilibrium with a hot temperature bar at a particular temperature T, and there is an external field applied in a certain direction on this atom. So what will happen is that first of all we have to calculate the average spin for this case, right? So right, so what was the question? So we have to calculate the mean spin of the system or the average spin of the system. So this is right. To calculate the average spin is equal to what? Okay, so just a second, there is a technical glitch I think. So just a second. Okay, so let's continue. So the question was that we have an atom sitting with in a hot temperature bath of temperature T, and it is in thermal equilibrium with that bath, and it is also in an external magnetic field Hm. Now we have to calculate the average spin, that is this S average for this kind of a problem. Now, now this atom can have either spin up or spin down, and correspondingly it will have S value or spin value will be +1 or -1, right? So let's say the atom has a magnetic moment of mu. So this is the magnetic moment of the atom. It can either have spin up where S equal to +1 or spin down is equal to -1. Now this atom, because it has a magnetic moment of mu and its spin is S, so you know that the magnetic moment is actually related to spin. So it will take the same sign as the spin value, because here the atom has no as such negative charge or anything mentioned. Like in the case of electron, you know that both are opposite directional because the electron is negatively charged. But in this case, no such thing is there, so you will just assume that your magnetic moment is parallel to the spin of the atom, which is S. Okay. Now you know that uh, the energy of such an atom which has a magnetic moment of mu, and it is sitting at a external field of Hm. So the energy in this case will be written as minus mu dot Hm. So these are vector signs, and this is the dot product between the two vector, magnetic moment vector and the external field direction vector, and there is a negative sign with that. So this is basically the energy expression. Now, depending on where how is this moment aligned with respect to the field direction, so this angle between both of them will be decided, and you have to calculate what is minus mu Hm cos theta, where theta is the angle between mu and Hm as the energy. Okay, so now in this case, when you know that atom is in spin up state, so then the magnetic moment is actually parallel to the field direction. So basically, your let's say your magnetic field was in the upspin direction, so it is in the upward direction magnetic field, and your atom can either be upspin or it can be downspin. So depending on that, the energy will be decided. So for the field which is in the upward direction, if the atom is in the spin up state, that means the atom is also in this up spin state. So then both Hm and mu are parallel to each other. So in the same direction, so your theta equal to 0 degree and hence cos theta equal to 1. And the energy of this up spin state will be simply minus mu Hm because cos theta may becoming 1. Now at this upward directional field, when atom is in spin down state, so that means there your magnetic moment, which is actually related to the spin, it will also be in the downward spin direction. So that means there it will be making an angle of 180 degree with the upward directional field. So then the theta value will be pi for 180 degree. So then cos pi is minus 1. So there you have the energy of the down spin state will be minus mu hm into minus 1, which is basically your plus mu hm. So, for this case, you have calculated what is the two possible energy states for the atom to occupy, and depending on whether the atom's spin or magnetic moment is parallel to the external field direction or anti-parallel to the external field direction, we have calculated the energy for each of the for each of the configurations, up spin or down spin. So if that is done, then you know that what is the partition function for such a system. So partition function is simply the sum over r e to the power of minus beta here, where r is denoting the state that are possible for this case. So here there are two possible states, spin up and spin down. So r is basically 2. So you have to sum over both the terms. So first term is e to the power of minus beta into minus mu hm, which is basically for the upspin state. And the second term is e to the power of minus beta plus mu hm, which is basically for the downstream state. So your partition function is nothing but the sum of e to the power of plus beta mu hm plus e to the power of minus beta mu hm. So this is your partition function. Now you have to calculate the average speed of this case. So average speed you have to use the e to the power of minus beta e term as the weight factor, like you use for the Boltzmann weight factor for taking averages, and then you have to divide by the partition function for the average calculation, right? So basically, first of all, for the up spin state, your S value is plus 1. So then plus 1 and the corresponding Boltzmann weighing factor is e to the power of minus beta of minus mu hm, which is basically taking it as beta mu hm at a plus sign. So this is basically corresponding to the energy level of minus mu hm. So this is the Boltzmann weighing factor for the spin of state, and that's why you have plus 1 at the front. Then for the second term, you have the speed going as -1. So you first take -1, and what is the weight factor for that speed state? Is basically e to the power of minus beta mu h. So this is for the energy level of plus mu h, which is for the speed downstream, and that's why it is remaining as a negative sign because there is a e to the power of minus beta giving it a negative sign. So this is the case, and then you have to divide by the partition function z. So the final answer is basically e to the power of plus beta mu hm minus e to the power of minus beta mu hm divided by your partition function value is e to the power of plus beta mu hm plus e to the power of minus beta mu hm. So this is your average spin value for this atom. So now you are, let us choose from the options given. What is the correct option? So correct option is basically e to the power of plus beta mu hm minus e to the power of uh, I think yeah, yeah, right. So e to the power of plus beta mu hm minus e to the power of minus beta mu hm divided by the partition function value. So this is option number 1 that we have to choose as the right option. Now let us go and read question number 3. It is asking that the Ising model can be mapped to which of the following physical systems? 1 is magnetic systems, 2 is lattice gas, 3 is binary alloys, and 4 is all of those. Now, here you know that this answer will be, first of all, it will be all of those, because all of them satisfy a condition that actually makes Ising model compatible to explain each of the systems. First of all, for magnetic system, it is very obvious that Ising model is obviously will be compatible or mapped to the magnetic system, because originally it is the model given for magnetic systems only. Because you remember that the Ising Hamiltonian has terms like SI, ST, etc., which are like spins, right? And spin is related to magnetization. We all know that. So basically, from there we know that it is basically. So what was it? It was minus j sum over ij nearest neighbor, then SI, ST, then minus external field of small h sum over of I SI. So this is related to spin, and the first term is from the exchange interaction between the strings, and the second term is the strings interaction with the external magnetic field. And if your J was greater than 0, so then it was ferromagnetic, and J less than 0, it becomes antiferromagnetic. That means very clear cut, this model is actually originally made for magnetic systems only. So the first option is obviously correct. So Ising model is originally solved for magnetic systems only. But later on we found, sorry, I think, yeah. But later on we found also other applications of the Ising model. There are other similar systems where the same Ising model calculation can be applicable, because they are somewhat analogous to the Ising model's main structure, which are, for example, like lattice layer system and binary alloy system. So how do we connect Ising model to them? So this is very easy. Basically, the main feature of this Ising model Hamiltonian is that your SI or spin value should be +1 and -1. So there are only two possible allowed values for the spin components, right? Two allowed values of the spin in this Ising model. Similarly, let us try to find the similarity of the other systems to actually know whether we can apply or relate Ising model to them. So let's say for lattice gas, we know that lattice gas has a lattice structure format where many of the lattice sites are occupied and some of the lattice sites are unoccupied, right? So let's say if you have a lattice-like structure like this in the lattice gas, so then some of the sites will be occupied, like I am doing with red maybe. So if these are the lattice sites are the vertices, so then you see that maybe these red surfaces are all occupied by atoms, but there will also be unoccupied sites where there will be no atoms present, like this, or this, or this, etc. So because we have again two kind of states present in this lattice gas system. One is the occupied state where the lattice site is occupied by some atom, and other is the unoccupied state where the lattice site is not occupied by any atom or it is vacant. So again, like spin up and spin down, two possible states of magnetic system where originally Ising model was applied. In the lattice gas system as well, we see that there are two possible states. One is occupied state and the other one is unoccupied state. So it has occupied lattice site, which is taken to be analogous to the spin up state in the is equal to class 1 state in the original Ising model Hamiltonian in a magnetic system. And the second state is your unoccupied state. So it is unoccupied lattice site, which is analogous to your downspin state or SI equal to -1 of the magnetic system. So by this similarity, we can directly tell that we can treat this lattice gas system similar to a magnetic system, and Ising model can be mapped in the system as well. Similarly, for option number 3, like binary alloys, we know that binary alloys are alloys which are made of two components. That's why the name binary. So it has two elements present. Let us name them by A, and element A and element B. So then in the whole structure of the alloy, there will be some portion of the some atoms coming from type A and some atoms coming from the element type B. So then again two kind of states are there, A state and B state. A state we can correspond to the spin up state. Let's say the SI equal to 1 state. So let's say for option number 3, which is for binary alloy, we can take the spin up state to be analogous to your to our element A of this alloy, and the down spin down state of SI equal to -1 of the Ising model can be mapped out to the B element in the system. So this is why also for lattice gas and binary alloy, we find there are two possible states that the system can be remaining in, and these two states are basically taken to be analogous to the SI equal to +1 and -1 state for the original Ising model applicable for a magnetic systems. So the option is correct option is all of these, that all the three options, magnetic systems, lattice gas systems, and binary alloy, all of them are suitable such that Ising model can be mapped to the systems to explain its physical properties. Okay, so this is the question number 3 that is being answered. Then question number 4 is that consider a one-dimensional Ising model with n spins at very low temperatures. So you have a 1D Ising model with total number of spins at n, and the temperature is very low. So then when almost all the spins are aligned parallel to each other, there will be a few spin splits uh, with each spin flip costing at an energy of 2J. In a configuration with R spin flips, the energy of the system becomes equal to -Nj plus 2Rj, and the number of configuration is NCK. So here there is a printing mistake, I think. So it should be not directly NCK, or it should be total number of spin if that is N, capital N. So then capital NCR, where the this part capital N is the total number of spins in the system. This C is basically take the combination, and R is the index that varies from 0 to n, the total number of spins. So then what is the partition function value? You have to choose from the options. Now let us solve this question. Let us choose a blank page again. So this is question number 4, and it is said that let's go to question number 4. So this is like a one-dimensional chain of atoms. That means it is like a one-dimensional chain with each atom sitting at each side, and we cannot see the end of it. Maybe it can go far else, but for the sake of the understanding, we say that this is from starting from r equal to 0 to r equal to n. Right? So there are total n number of spins are present. Right? So this is like a one-dimensional chain of spins, and your total number of spins is capital N. So you know that the energy is given as the expression of minus mj plus 2 rj, where j is the exchange interaction strength and n is the total number of spins, and r value can go from 0 to n. So let's say for n equal to 1 case, when the total number of p is only 1, so then your energy becomes minus j plus 2rj, because we have substituted n to be 1. Now, if n is 1, then r can also take values only from 0 to n. So, it will take values from 0 and 1, because there is only for the integer signs applied, integer values. So, we have to choose only 0 and 1. And if it is chosen as 0 and 1, so then for r equal to 0, the energy state is simply minus j. And for r equal to 1, the energy state is minus j plus 2j, which is plus j. So for a single spin, this is the configuration possible for the where r denotes the spin flip times. So this is for r equal to 3, you have an energy state of minus j, and for r equal to 1, you have the energy state of plus j. Okay, so basically these are the two possible two allowed energy states of the system to be in. So there are two energy levels, right? So this is the this let's say. So you have minus j, then you have plus j. So if you have only one spin or n equal to 1, then it can either be here or it can be here as well. Okay. So if you have to calculate the partition function for this n equal to 1 case, so then z n equal to 1 equal to e to the power of minus beta er, where r value 0, er, so this will be from r equal to 0 and 1 e to the power of minus beta er. So it will be like e to the power of minus beta e0 plus e to the power of minus beta e1. So it is e to the power of minus beta minus j plus e to the power of minus beta plus j. So this is like e to the power of plus beta j plus e to the power of minus beta j. But then sometimes the partition function are also taken when the averaging factor of the count is written in the denominator, right? So your partition function for z in at n equal to 1 will be like this partition function divided by the number of combinations possible, which is basically your sum over NC or NCR. So basically this partition function becomes, so if this is like small n equal to capital N, that n is the total number of spins, and this is NC, and for r equal to, you have to put 0 and 1. So you know NC0 equal to 1, C0 is equal to 1, equal to just 1, and NC1, which is like 1C1, which is again like 1. Okay, so you get your partition function for a single spin equal to, so it equal to e to the power of plus beta j plus e to the power of minus beta j divided by sum over NCR, r value from 0 and 1, which is like e to the power of beta j plus e to the power of minus beta j divided by 1 plus 1, which is like 2, right? So for a single spin or n equal to 1, your partition function final value is like, say n equal to 1 is equal to half to the power of beta j plus e to the power of minus beta j, which is like cos of hyperbole beta j. Now same thing, if you try for n equal to 2 or 2 spins are there, then What are the possible values? First of all, if there are two spins, then how to organize uh, which will be the energy states in this case. So there are two spins, right? So it will be like either, so the R value will be going from 0 to n, and means it will be going from 0, 1, and 2. Three values are there. So your R value will be like uh, 0, 1, and 2. And in this case, the n capital N equal to 2, so the energy levels will look like for R equal to 0, energy level is equal to still minus mu, sorry, not minus mu. So the energy level will be e to the power of minus, no, sorry, the energy level is, one second. So the energy level, in this case, we know the expression equal to minus nj plus 2rj, right? So this is R. So it is minus nj plus 2rj, and n equal to 2, so it is minus 2j plus 2rj. So for R equal to 0, equal to 0. Sorry, for R equal to 0, equal to not 0, so it will be like minus 2j. Okay, some problem is happening. So it is just minus 2j plus 0, which is like minus 2j. And for R equal to 1, equal to minus 2j plus 2j, which is like 0. And for R equal to 2, equal to minus 2j plus 4j, equal to plus 2j. Okay, so let's start this problem over. So I think there is some confusion. So for n equal to 1 spin, n equal to number of spin 1, we have chosen R equal to 0 and 1 because that is the rule that R has to be 0 to n. Then accordingly, we had also calculated what are the energy values corresponding to R equal to 1 and R equal to 0. So we got for R equal to 0, if you put the expression of energy formula, and if you plug in n equal to 1 and R equal to 0, you get minus j as the energy. And similarly, if you plug in n equal to 1 and R equal to 1, then you get plus j as the energy. So there are two allowed energy levels, and the corresponding partition function, if you need to calculate, then if you get this thing, that is half of e to the power of beta j plus e to the power of minus beta j, which is nothing but cos hyperbolic beta j. Same for n equal to 2 spin, you get r from 0 to n, that means 0, 1, and 2 in integer interval of r values. And for each of the r value, you have to calculate the energy value. Let's say for r equal to 0, your energy, according to this formula, plug in n equal to 2 and r equal to 0. So then this is minus 2j plus 0, which is simply minus 2j. And for r equal to 1, you get equal to, plug in n equal to 2 and r equal to 1, which is 0. And for r equal to 2, you get equal to, plug in n equal to 2 and r equal to 2, which is plus 2j. So these are the three possible energy values corresponding to this. And you have to also again calculate the partition function like the earlier one. And so the formula that is followed in this case is basically uh, some kind of averaging of the partition function, meaning that you not only have to take this form, that sum over r e power of minus beta er, where r is the denoting index for different energy values that are allowed for this case, also divided by sum over total in C R, where r equal to from 0 to n. Here also r equal to from 0 to n. So this is the combination values for all the possible number of energy states that you are dividing in the partition function in the denominator, and that is the idea. You have the formula you use for the partition function. So we use here for r equal to 0, it is e to the power of minus beta times minus 2j as the energy. So it makes it plus 2 beta j. Then again plus, then r equal to 1, energy value is 0. So it is plus e to the power of 0 simply. And the third term is for r equal to 2, which is energy value is plus 2j. That means it is e to the power of minus beta times plus 2j, making it minus 2 beta j, right? And the denominator makes it, this is n. So you, in this case, your n is fixed to be 2, right? So this is 2. And the r value can be 0 and 1 and 2. So we have three terms, 2c0 plus 2c1 plus 2c2. Now you know that combination rule gives you that 2c0 is nothing but 2 factorial by 0 factorial 2 factorial, which is equal to 1. Similar for 2c2, if you calculate, you will also get 1. But for 2c1, you have 2 factorial by 1 factorial and then 1 factorial. So here you get 2. So also, yes, I think I missed one thing, that is that you have also to include the weight only, not only the e to the power of minus beta j term, but also you have to like take how many times each of the term appears. Like for e to the power of plus beta j, it only appears one times because here 2c0 is 1. So this is 1 into this thing. Then for 2c1, you get that here 2c1 equal to 2. That means the r equal to 1 level appears twice, 2 times. So we have to multiply here by 2. And also because you have to take the degeneration of each of the level, right? So that is why. And for r equal to 3, r equal to 2, you have the 2c2 value as 1. That means here the number of combinational values is 1. So it is 1 times this thing. So the whole thing becomes e to the power of plus 2 beta j plus 2 into e to the power 0 is 1 plus e to the power of minus 2 beta j divided by 2c0 is 1, 2c1 is 2, and 2c2 is again 1. So it is 2 plus 1 plus 1, that means 4. So the total thing is partition function expression is 1 by 4, 2 plus e to the power of plus 2 beta j plus e to the power of minus 2 beta. Now if you look carefully, you will see that this is nothing but the square of this form, to the power of plus beta j plus e to the power of minus beta j divided by 2 whole square. So this 2 whole square makes it 4 in the denominator. And also in the like numerator you get this e to the power plus beta j plus e to the power of minus beta j whole square is basically a square plus 2ab plus b square formula. So making e to the power of plus 2 beta j plus 2 times e to the power of beta j into e to the power of minus beta j plus e to the power of minus beta j whole square, making it e to the power of minus 2 beta j. So it is basically e to the power of 2 beta j plus 2 into 1, that means 2, plus e to the power of minus 2 beta j. So this is your whole thing, which is like this thing. So you are getting the expression of n equal to 2 partition function as this. So if you remember that for n equal to 1, your partition function value was simply cos hyperbolic beta j for n equal to 1. So for n equal to 1, your partition function for n equal to 1 is cos hyperbolic beta j to the power of 1, or in other terms you have cos hyperbolic j by kbt to the power of 1. And for n equal to 2, we have just calculated that the partition function value then becomes equal to, okay, so this value is, we know that cos hyperbolic beta j, right? This beta e to the power of beta j plus e to the power of minus beta j by 2. This is nothing but your cos hyperbolic beta j, and there is a square sign later, so you get the whole square of cos hyperbolic beta j. That means the partition function z for n equal to 2 is cos hyperbolic beta j means j by kbt. This thing's whole square. The power is 2. So just like that, if you continue, you will see that for n equal to 3, your partition function value will be cos hyperbolic j by kbt to the power of 3, right? So if you just uh, yeah, so if you just continue and by the process of mathematical induction, you will automatically get the idea that the general expression is that the partition function for general in number of speeds will simply be z suffix n equal to cos hyperbole j by kbt to the power of n. So corresponding to how many number of uh, particles are there or speeds are there, depending on that value, the same power will be the power of the cos hyperbolic function in the partition function expression. So this is our answer. So let us choose the correct option from the options given. Um, yeah. So this is the option number 4 is your correct option, right? So option number 4. Then question number 5 says that consider a system of three classical spins S1, S2 and S3, each of which can take values only plus 1 and minus 1, which is like Ising value, right? Ising spin can also take plus minus 1 value only. So the energy of the system is given by equal to minus j times S1 S2 product plus S2 into S3 product plus S3 into S1 product. That means it is basically your minus j SI kind of a term where S1, S2, S3 all three are nearest neighbors of each other and therefore it is taken like a combination of all the three products. And also there is no external field term. Maybe the external field is not present or h equal to 0. That is why only this exchange interaction term is present with the strength of exchange interaction as J. So here it is said that J is positive constant. That means J is greater than 0, which signifies that it is a ferromagnetic type interaction. And it is asked that what is the minimum energy and the corresponding number of spin configurations for this kind of a case. Right. So let us go to a new page. So your question number 5 says that your energy for the system is minus J S1 S2 plus S2 S3 plus S3 S1. And also your J is greater than 0. Where J is your exchange interaction strength, and if J is greater than 0, it means that it is an FM or ferromagnetic type interaction. Okay, because that will only lead you to the minimum energy state, which is the stable state. And for this case, it is also the information available to you that S1, S2, and S3, each of them can take only two possible value of spins, either plus 1 or minus 1. So then, if your J is greater than 0, so then you know that the minimum energy state will be when the spins are all parallel to each other, right? So all three spins, S1, S2, and S3, all are parallel to each other, either in spin up state or in spin down state. So either all of them are, all three are spin up, which means all S1 equal to S2 equal to S3 equal to plus 1, or all of them are spin down state. So all three are spin down state. That means S1 equal to S2 equal to S3 equal to minus 1. So this is the case, right? So then if that is the case, and this is happening because we have been given the information that this is a ferromagnetic type of system because J is a positive constant. So now if that is the case, then your S1, S2 or S2, S3 or S3, S1, any of the product will always be plus 1 only. Because either they both the spins are plus 1, then the product is by default plus 1. And or if both the spins are minus 1 or down spin, then also their product becomes plus 1. So all these products are plus 1 always. And it was asked that then in this configuration, what was your total energy for the system? So the total energy is, according to this expression given, minus K times S1 is 2 is plus 1, S2 S3 is plus 1, and S3 S1 is also plus 1. So this will be minus 3J. So this is the total energy, and it is also the minimum energy corresponding to the ferromagnetic stable state configuration. This is the minimum energy also. This is the total energy of this configuration. Now, also it was asked that how many configurations are possible. So we already drawn it that there are two possible configurations, either all of them up or all of them down, right? So this is configuration number 1, or all of them down with it is configuration number 2. So the answer will be your energy value is minus 3J, and number of configurations that are possible in this case for this given conditions are 2. 2 possible spin configurations, and here it is the total energy is minus 3J. So let us choose the option. So the option is minus 3J and 2. So the option is number 3. This is the option, right? Then the question 6 is that when an atom is placed in a solid, the interaction of charges with non-magnetic atoms surrounding it creates whichever option you have to choose is the correct option. So basically, it will be the answer will be a crystal field. We had already studied it before in the lecture session that because the atom is placed in the solid and it is interacting with the charges of the surrounding non-magnetic atoms. So it is basically a crystal field effect, also known as. So it is not basically related to the magnetic property of the system because clearly it is the interaction of charges with non-magnetic atoms, right? So it's the interaction of charges with non-magnetic atoms. So it is kind of an electric field effect, you can say. So this is like um, non-magnetic atoms. So this will be causing you a crystal field. So I'll not go into the details of it because this is the conceptual idea that is probably done in the lectures. So this is the idea that this is the crystal field effect because this is the interaction of charges with non-magnetic atoms surrounding a particular atom in a solid. Now, question number 7 is that it is a also mathematical type question. Let us read this out. So consider a one-dimensional open chain with Ising model, open chain Ising model with n spins in an external magnetic field H. So you have a 1D Ising model like open chain. So basically your Ising model can have different structures based on how you want to solve it. So it can also, some people also take closed chain Ising model like a periodic boundary condition to be applied. And it can also be solved by a open chain Ising model, simply like a one-dimensional chain with both the ends are open and no periodic boundary condition in that case will be applied. So both of the cases are possible. So in this case, it is given that it is a open chain Ising model. Total number of spin is n, and the external field and spins are sitting in H. Okay. Now each spin will interact with its neighbor and with the external field. That means both the two terms in the Ising model Hamiltonian will be present. Now choose the correct expression to calculate the energy of a microstate of the system. Also, the hint is that in this state different from the closed chain Ising model, the first chain does not interact with the nth. The first spin does not interact with the nth spin. Now we have to choose what is the correct option, and here J is your exchange constant, and SI denotes the ith spin. Okay. So question number 7. First of all, you have to understand this is not a closed chain Ising model. So this is a closed chain Ising model, and this is the open chain Ising model. So in closed chain Ising model, what happens is that let's say in both of the cases you have total number of spins in the model as n. Okay, so that does not change. Only the structure changes from closed to open. So if the total number of spin is still n, so then let's say we start with S1, then S2, then S3, and so on. If you continue, at a time you will reach at the last spin, which is your Sn, the nth spin, because you have total n number of spins. Now, after that, your chain does not end because it is a closed chain system. So the n plus 1th chain is not some separate. So the in the chain, the n plus 1th spin is not some separate new spin, but it is same as the first spin that we started with in the chain. So Sn plus 1 equal to S1 in the closed chain Ising model of total n spin. So in this kind of system, one can apply periodic boundary condition here to solve periodic boundary condition in such a closed chain system to solve. And what is your periodic boundary condition? Which is nothing but this, that your n plus 1th speed is not some new speed, but it is same as the first speed, because you are going back to the same point when you are in a closed chain. So your periodic boundary condition was is n plus 1 equal to s1. So this is the periodic boundary condition one can apply to solve the closed chain Ising model. Now also there can be a one-dimensional open chain Ising model with the same total number of spin n. To compare that how both of them are different, we are taking the number of spins to be same for both of the structures. So this is total in spins. So if you start with, let's say here this is S1, then S2, then you have S3, and if you go on, at a point you will end up with the last spin and no spin left anymore. So this is the nth spin Sn. So in this case, you can see that this is because of the open chain Ising model. So this S1 and Sn are at the both extreme ends of that chain. If you consider it like a one-dimensional chain, and the spins are like different parts of the chain, then the two extreme ends of the chain are positioned for the two spins S1 and Sn um, at the two extreme edges. But the in-between spins like S2, S3, etc., all of them had to have two neighboring spins on both the sides. Like let's say for S2 here, for example, let's say for S2, you have on the left one spin S1 and on the right one another spin S3. That means S2 has two nearest neighbor spins on both sides of it. Similarly for H3, if you know that here there is H4 also present, which I had not written down earlier, but it is present, that is meant by this dotted sign. So then H3 has on the left H2 spin and on the right it has H4 spin. That means H3 also has two nearest neighbors on both the sides of the spin. And this continues for all the intermediate spin values except for the leftmost and the rightmost spin value sitting at the both extreme ends of the chain. Because S1 has only on the right it has S2 spin, and on the left there is no spin present. So it has only one neighboring spin, which is S2. Similarly for Sn, you have only one neighboring spin, which is just the spin before that, which is S. But on the right of the Sn, there is no spin present because it is the end of that chain. So both S1 and Sn have only one nearest neighbor, whereas all the other intermediate spins have two nearest neighbors, right? So based on this idea, we'll calculate now the energy or the Hamiltonian for this open chain Ising model. So only S1 and Sn have a single nearest neighbor in dot in spin because they are sitting at the extreme edges of the 1D chain. And nearest neighbors, all the other spins like S2, S3, continuing up to Sn minus 1 have two nearest neighbor spins, right? So now we have to calculate the energy for such a structure or the Hamiltonian for such a structure. Now you know that the Hamiltonian or the energy for the Ising model has this common form, that is minus J sum over all the nearest neighbor spin values Ij nearest neighbor, then Si, Sj are the nearest neighbor spins, minus H, capital H, which is basically the external field that the spins are sitting in, then sum over the individual spins, and I equal to from 1 to n, total n number of spins. So this is the standard structure of the Ising model Hamiltonian, giving you the total energy For nearest neighbor, you only have, if you let's say are talking about the spin SI, then you have nearest neighbor only as SI plus 1, right? So you only have SI plus 1 and the next nearest neighbor for the spin SI. And here the I value will be going from 1 to n minus 1. Okay. And there will be also a negative sign. Why we are choosing I plus 1? Because for a particular SI somewhere present, let's say if SI equal to 2, then your next nearest neighbor will be SI plus 1, that means 3. Similarly, for I equal to 1, you start with I equal to 1. So then SI is S1 and the next nearest neighbor is SI plus 1 or S2. And similarly, you cover up to all the strings up to Sn because there I goes from 1 to n equal to n minus 1. You have Si into Si plus 1 as Sn minus 1 times Sn, which is the last term. So that is how you cover all the strings in this nearest neighbor position of this one-dimensional open chain case. And the second term is minus sum over I equal to from 1 to n Si. So this Si into Si plus 1, how it is written, I have already told you, but still I write down once again that it is for I equal to 1, this is S1, S2. Then for summation sign, so this is plus. Then for I equal to 2, this is S2, S3. For I equal to 3, this is S3, S4. Plus it continues up to I from I equal to n minus 1. So this is Sn minus 1 into Sn. And there all the spin values are exhausted. So this is the extreme interaction term coming from the first term. And for the second term, if you want to break it down and decompose in a two different spin structure. One is the actual spin, one is the spin's nearest neighbor. So you can write it down like minus h sum over Si plus Si plus 1. When here the I value has to go from I equal to from 1 to n minus 1. Because you are writing down this minus h sum over I equal to from 1 to capital N Si as some other simplified or decomposed format, which is like minus h to sum over from I equal to n minus 1, I equal to 1 to n minus 1, then Si plus Si plus 1. So particular spin Si and the neighboring next neighboring spin Si plus 1. And then to compensate, to adjust for the extra values, you have to also take like say here, if you just calculate what is this value, you see that this is minus h, then S1 plus, for S I am saying S1 plus H2 plus up to S in minus 1. Then for Si plus 1, you start from I equal to 1. So this makes it I 1 plus 1, 2. So you start from H2, then S3, plus it continues up to n minus 1. So I n minus 1 plus 1 makes it Sn. So you see that except for S1 and Sn, all the other terms are coming twice. Like S2 coming from this sum over Si term initially, and then also coming from sum over Si plus 1 term later. Similarly, for S n minus 1 term will also be coming here before Sn. Okay. So all the other terms will also be coming twice except for the two extreme terms S1 and Sn, because basically minus h by 2 S1 plus S2 plus, so this is basically 2 times all the other spins and 1 time S1 and S2. So this is basically, just write it down like that. So minus 8 S1 plus 2 S2 plus 2 S3 plus dot 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 plus 2s in n minus 1 plus single Sn. So this is the case, and then you can just convert it to the minus h by 2 Si plus Si plus 1 sum over I equal to from 1 to n minus 1. So if you take a divide by 2 in the denominator, so then all the two factors present with S, compensate it, and you will directly get S2 plus S3 plus the other spins without the two factors. That's why you divide by 2. But also, you will end up with a minus HS1 by 2 and minus HSN by 2 as an extra factor. So, we have to compensate for that, right? So, for that, we like take out the other two terms as minus H by 2 S1 and minus H by 2 SN. Okay. Alright. So yes. So basically, if you just take another minus 8 by 2 and minus 8 by 2 is 1 and SN term, then the whole term becomes equivalent to writing it as minus. So just check for yourself also that this is actually coming as valid. Also, let me show you once again. If you just compare LHS or RHS, whether they are equal or not, then you will see that actually we can write this term in this separate form like this above expression. So like say if you have this RHS, which is this thing, is simply as minus H S1 plus S2 plus S3 plus dot 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 plus Sn minus 1 plus up to Sn, right? Then for LHS, if you compare what is the LHS value, you see that this is again minus H by 2. Then this Si plus 1 going from I equal to 1 to n minus 1. That means S1 plus 2S2 plus 2S3 plus all the other things as 2 factor that 2S in minus. And also you have, sorry, then we have 2 sign which is removed from here. So this is minus H by 2 S1 also is there and minus H by 2 Sn also is there. So you end up with this 2 factor and 2 factor cancels out for all that intermediate speed values, and this minus H by 2 S1 into 2, this y factor coming because we had extra S1 and Sn term to compensate for that. So then again similarly minus H by 2 S2, sorry, minus H by 2 Sn into 2. So these two factors are already compensated out from the extra terms here, and the other rest of the terms are compensated by the bracketed divided by 2 and the extra 2 factors. So this is again minus H is 2 plus H3 plus up to is in minus 1. So the whole thing turns out as minus other terms like is 2 H3 plus up to Sn minus 1, and the last term is Sn. Okay, so that is how I am showing you that you can rewrite your this expression as this new expression. Okay, so if that is the case, then we can just form our total energy for this structure, that your total energy E is equal to simply minus H by 2 S1. So you take this minus H by 2 S1 first, then you take the external interaction term and the external field term, which is like, sorry, which is like sum over I equal to from 1 to in minus 1, then j is I plus 1, the external interaction form plus is I plus 1 minus h by 2 Sn. So we just write the these two extra terms at front and at the end, and the rest of the terms are these terms which I had already shown you that you can rewrite in this form. So this is the term and decomposed term, and the first nearest neighbor interaction term is Si into Si plus 1 with j. So this is the last expression that you achieve if you are to write the total energy for such a combination of in a system. So let's choose our option then. Here option number is option number 1, because you can check that this is exactly the same as the answer we obtained. Now, question number 8 says that using the Ising Hamiltonian with the standard form, we already know what is the standard form of Ising Hamiltonian, and J is the positive ferromagnetic coupling neighbors. which we know that nearest neighbor denotation is only denoting is only done by this hard bracket, this kind of a bracket with ij sign, and SI equal to plus one or minus one if the is the speed of the ith side. H is the external magnetic field pointing along the z direction, and N is the number of sides on the lattice. Choose the correct expression for the magnetization. So we know that the magnetization is nothing but your total average spin value, right? So if your each of the spin is denoted by SI and it can take either plus one or minus one value. So you cannot choose both. So you have to take a average of those values. So you have to take an average of SI, which is this sign, SI average, and then you have to sum over all the n values, all the n number of sides from 1 to n, I equal to from 1 to n, and then you average it out by the total number of sides, which is again average total spin per side. So this is your 1 by n sum over I from 1 to n is I average. Okay, this is the answer. Now question number 9 is that in a triplet configuration of two electron ground state, the maximum value of total spin is, we know that the answer is very easy. This answer will be s equal to 1, because in a triplet spin configuration s value is always coming as 1, because the spins are like either this or this, or the third one is this. So here the triplet configuration is, and according to the ms value, that means the z component of the spin angular momentum value will take from um, minus s to plus s. That means it is minus 1, 0, and plus. So this is the triplet configuration answer, that the total value is equal to 1. Similarly, for a singlet state spin configuration, the total value of is the maximum possible value of total spin will be just 0, because there the spins are oppositely directed to each other. So there the spin will be 0, is equal to 0. So is equal to 0 for singlet and is equal to 1 is for triplet. And question number 10 says that for two electrons, the spatial part of the ground state is what? So for two electrons, that means they have to follow or abide by the Pauli's exclusion principle. That means two electrons with the same spin state. So the total entire wave function for the electrons will have to be antisymmetric or asymmetric, because uh, that is occurring from the rule of quantum mechanics that is happening in this case. That is something related to exchange symmetry. Exchange, I think this is called asymmetrization or something, where the total wave function for the electron will have to be asymmetric. So the total wave function has two parts, spatial part and the spin part. And because the two electrons are sitting together in the ground state, so we have to choose that their spins will be opposite to each other. That means they are in a singlet state or is equal to 0. So if spin wise they are asymmetric state to each other, so then spatially the state has to be symmetric, so that the entire wave function is a combination of both spatial and spin part, and that turns out to be asymmetric. So this is the to follow the spins are singlet spin state and it's equal to 0. So the part will be triplet or symmetry. So singlet state is antisymmetric and spatial part is symmetric or triplet. So the answer is triplet. And why so happens is that so that the Pauli's exclusion follow. Okay, so that is why if the spins are taking a singlet state or up and down configuration for 2 electrons in the ground state, so then obviously the spatial part will be a triplet state. Okay, so basically we have covered all 6 questions. Let me stop the class here and let me know in the if you have any doubt in any of the questions, then let me know in the next session of tutorial, or you can also let me know through email in the course forum. Okay, so